Good morning, everyone. Today we are going to discuss logistic regression. I know some of you are eagerly waiting to learn this topic so that you can complete or conclude your analysis for the final project. So let's go on. I'm going to turn my video off so that you can see the full screen. Okay. So first things first, let's because we need some sort of the data set to run some examples. So let's just get the data and we'll use the same data that we used before. Uh, PBC data, and I'm sure you're familiar with that. So, but today we are going to use PBC sequence data just for a change. So you can change the check the structure. You can click on here. You can check it as well. But the better way to do that, I prefer, is you can check the structure over here and understand the what the variable types are. But again, you can also go on the help menu as well because to understand what are the PBC sequence data and what are the variables in that. And again, I'm not explaining how I got there because I'm sure you already know that by now. But just understand the formatting, what the data set is, um, and compare that with the data dictionary mentioned here in the help menu. Okay. Um, so we are going to use couple variables from the data, obviously not all. Uh, so let's just look at some variable. So I think I'm going to use the TRT variable for sure. So TRT is randomization. So either someone got the drug penicillamine or the placebo. Not randomized means they're not part of the trial, like that's missing. So this is a binary variable, and I want to see how that is coded. So as you can see, TRT is and currently it's a integer continuous variable that I need to set as a factor binary variable. Okay, so let's check the frequency distribution first. Because another variable that we would be looking at is this is the one hippedo. Let's just assume that let's just assume we'll take this as our outcome variable. So it's a presence of hepatomegaly or enlarged liver. So if for instance if a patient has an enlarged liver, that will be coded as 1. Patient does not have a enlarged liver, then it will be coded as 0. So that's a binary variable as well. So again, the hipero is also integer that I need to change that uh, as a factor. So I'll just put that hipero, and we can change. You can check the class with the class statement as well. Uh, but let's check the structure again. So hipero is factor and the TRT is factor variables with 2 levels as well. Okay, so that makes sense. The cholesterol, we have used this variable before from the other data set, like the previous data set, the PBC data set, the main one. So cholesterol is a continuous variable. It should be continuous variable in the data dictionary as well, which is indeed the case. So let's first start with logistic regression. Again, we are going to use hippeto. If the patient, what are the variables that predict the hepatomegaly or the enlarged liver? Because that's a pathological condition that is associated, that could be predicted by certain variables. So let's try to see. Again, this is a hypothetical data. Again, don't go with the research question. Don't go with the variables that we include in the regression model and so on. Just the intention here is to show you how we can build the regression models, how we interpret the results. And that portion, not the variables or the research question itself here. Okay. So first of all, because we are going to use the hepatomegaly as our outcome variable, let's check the distribution first. And the reason we want to check the distribution is that because if the distribution is very like if there are only few observations here in one of these either levels, it will result in unstable logistic regression models. So you kind of need some sort of the fair distribution. Now, if you're wondering like what is a fair distribution, are there any cutoffs? They're not really. I don't think I came across any specific number or magical number that I can share with the class. Uh, but I think I would say you need kind of at least 70-30 or 80-20% distribution at least. If you have something like this, that's a beautiful distribution for to run the logistic regression. But if you have like 1% observations in one level and 99% of the observations in other level, that will definitely result in unstable regression models. So uh, that's that's something to keep that in mind. Okay, so we check the distribution, looks okay. Now let's build the logistic regression model. To build the logistic regression model, it's nothing much different. Like if you know how to build the linear regression models, it's pretty much the same efforts that you need. You don't need to do a lot more different work to build the logistic regression uh, in RStudio. What you need to do is that you need to understand the theory behind it. If you understand the theory, that is a great part. Because remember, I said that in the beginning of the class, it's the more effort that we need in analysis in terms of the getting the data ready, cleaning it, transforming it, importing it. Those are the stuff. Cleaning the data in particular, it requires far more uh, work than the building the regression model itself. So in order to build the logistic regression, we are going to use the generalized GLM model. Like if you remember that if we did use the LM model for the linear regression, now we are using the generalized linear model. So how this model GLM are different? So it is still a generalized linear model. Uh, so instead of now LM function, we will use the GLM function. So the difference between the two is that the GLM function allows us to build the regression models that do not meet certain specifications that are required for linear model. Like for instance, is having a binary variable. We cannot build the well linear regressions if you have the binary distribution of the outcome variable. But the GLM is still generalized linear model. It still allows us to do that. It still allows us to build the kind of a linear regression even with the binary outcome as well. So and again, if you recall the scatter plot, and again, I'm not sure if I have the scatter plot here or not, but if you recall the scatter plot in theory that we talked about, that the bronchopulmonary dysplasia and the birth weight that we had on the scatter plot, um, it, there were scatter plots like on the two different points, but you can imagine the regression line would be something that would go in between them. So that is the reason why it's a more generalized version of the linear model that allows us for non-normal, some untraditional kind of variables or the to build. It allows us to build those are the models. Okay, so not everything else stays the same, right? So we'll say again, this is where I'm going to save the model, like the object. And again, I'm using now, because for logistic regression we'll use the GLM function. This is generalized linear model. So I'm going to use the Hipero is my y variable, as you know, and so that's this is my equation. This is my y variable before the tilde, after the tilde, and I'm saying that let's start building with the one continuous predictor with the cholesterol. If I want to see if the serum cholesterol levels are uh, associated with the hepatomegaly, is serum cholesterol level is an important predictor for hepatomegaly or not. If that, let's just assume this is my research question. So this is your y variable, this is your x variable after tilde. Okay, now this is something different than we didn't see with the linear regression. I'm specifying that now family is equal to binomial. I'm saying that it's a binomial distribution for logistic regression. So once you do binomial distribution, uh, you can run and you can specify, like for instance, is you can also write the binomial in quotes like this, and in the bracket you can specify link is equal to logit. By default, link will be logit when you specify the family is equal to binomial. Okay, now, if you're wondering what other link you can use, there are other link options, the log, but it will not work with a binomial. You need Poisson distribution for that. But you can run the probit link as well, which is a probit regression model. We'll cover, I mean, that should be covering the biosets too. Don't worry about it. But here, I think what you need to know is that family is equal to binomial, link is equal to logit. That's something that's because why it's a log function. Remember, it's a log odds that we are discussing, right? So we just have to specify the family in here. I think the good practice is that you also specify the link in there as well, but it's by default, so I'm not going to specify it here. But for a final paper, make sure you specify the link as well. So you run the regression model. This is how you build the logistic regression. As you can see, it's not substantially different uh, than how we ran the linear regression. Now, because I ran the code, I don't see any error. I see the model in here. In order to see the results, you have to call the summary of that model. As you can see now, the summary, I'm going to expand this window a little bit. Uh, okay, so as you can see here, the first thing, now let's interpret this. What sort of output do we get here? So this is where like it our studio reminds us what's of the model we built, what's of the equation we had for the regression model. So it just reminds us that your y variable is Cepeto and your x variable is cholesterol. You build this regression models using the logistic regression family binomial. This is the deviance residuals. So as you can see, this is the minimum, first quartile, median, third quartile, and maximum. So this is the distribution of the deviance residuals. Again, just kind of a similar concepts with the linear regressions, how the residuals are, deviance residuals are distributed with the data. Okay, so this is, this helps us understanding the fit of the model. We'll talk about that in a while. These are the coefficients, the most important part of the regression model. And this is the estimate. It gives us a standard error. You know what the standard error means, right? What the standard error is that error that is associated when we measure this particular estimate, because this is a predictor. This is an estimator of the population parameter, right? And that the error is associated with our sampling strategy as well. So like there are always some error when you draw a sample from a population. So this is a standard error in this estimator. Could be. This is a z-value for the hypothesis testing, and this is the probability distribution for the hypothesis testing. What do you think is the hypothesis testing here? Here, the hypothesis testing is that the slope, I'll call the slope, like we used to call it the linear regression, is equal to 0 or 1 here. What is this? Recall the function, like the equation of logistic regressions in theory. And if you can connect that with here, that would be excellent. Is this the odds ratio? Can we say odds ratio is 0.2%, 0.21553? Excuse me. Uh, no, this is not an odds ratio. Why? This is a log odds. Remember the equation of the logistic regression. Again, if you're confused why this is not an odds ratio, make sure you go back to the theory lecture and understand the equation of the logistic regression. This is a log odds. So if this is a log odds, what is our null hypothesis here for the z and the p-value? Null hypothesis is that this log odds is equal to, because remember when odds ratio is 1, then there is no association between exposure and outcome. That's clear, right? So what is the log value of 1? Oops. What is the log value of 1? 0. Make sense? What is the log value of 1? 0. So this is, if this is a log odds, that means our hypothesis, null hypothesis, is that the log odds is equal to 0. Okay, and the alternate hypothesis is that the log odds is not equal to 0. And this is the hypothesis testing, the results of the hypothesis. This is the p-value, and then the R gives you the significance levels. It helps us easily identify the significant, statistically significant ones than the one they are not. As you can see, there are 3 asterisks. The p-value is significantly lower, right? Significantly lower. So it's a very strongly statistically significant. So this is, again, this is estimate, this is standard error, this is z-value, this is the probability of the hypothesis testing. Like these are the hypothesis testing that we have covered throughout this semester. Now, this is an estimate of the slope, sorry, call the slope. This is an intercept. This is an intercept. You know what the intercept means, right? When y is equal to 0, sorry, when x is equal to 0, then the beginning point of the value, I think we covered that in the class, that value is called the intercept. Now, we don't usually interpret, and I think I did cover that in the linear regression as well. Don't worry about this. We don't usually interpret this number in health research. Okay, there will be only a few occasions where you interpret that, but again, you have to fix this because again, sometimes it would not even make sense to you. Okay, so this is the hypothesis testing for intercept, which is you don't. I think very less likely you will interpret that for a final paper. Anyways, this is the most important part. Uh, this is our important predictor variable. We wanted to see if the cholesterol is a predictor for hepatomegaly. If there is a high serum cholesterol level, is this associated with the enlarged liver or not? So this is our estimate. This, remember, this is a log odds. This is a standard error, and this is a z-value and the probability of the hypothesis testing. Now, as you can see, what first of all, how do we interpret this estimate? Again, go back to the theory. It means that every unit increase, so like cholesterol, what is the units? It should be milligram per deciliter, as you can see here. Oops, let me highlight this. Yeah, milligram per deciliter. So that means that every 1 milligram per deciliter increase in serum cholesterol, the log odds of hepatomegaly increases on average by this number, right? By 0.215553%. Make sense? Again, why if you, I think even your textbook sometimes doesn't cover the on average increase. I think it does cover with the linear regression, but probably not, or many textbook they don't include the one on average in the interpretation. And I'll tell you why it is so important to incorporate that as well. As an example, for instance, if you say, if you take out that word on average from the interpretation, what difference does it make? That means that I'm saying that with confidence that every 1 milligram per deciliter increase in serum cholesterol increases the log odds for the hepatomegaly by this percent. Now, the problem here is that the whole concept, remember, the whole concept of the regression lies on the fitted line, right? We fit the regression line, and there is a method of the least squares we discussed in the theory. If you recall that from the linear regression, we talked about that. That means that, remember, not each and every observation. Yes, ideally we want all the observations of the data points to be on that line, but that's not going to happen in reality. That's the reason why we have the residuals, right? So because remember, it's not all the observations will fall on that line. That means that for each, and it's not that for, that means that let me explain that in a simple layman terminology. For instance, we can really tell that every 1 unit increase in cholesterol will increases the risk of the log odds of the hepatomegaly by this person in each and every person. Remember, not in each and every person. Regression is the fitted line, means that on an average, if you take the sample, on an average within the sample, the risk on an average, it goes up by that. Make sense? So that is the reason why the on average word, it's really important, because it's not going to be for each and every case. And that is the reason why, when, for instance, if you go to see a physician, for instance, they may say that what is the if you are going through the what is the prognosis, it's if that's a build from the regression line, it's not that if that number will truly applicable to you as well. Remember, we are looking at the population level data, right? So it's an on an average. For an individual, it could be much less, it could be much higher, but when we look at that collectively on an average, it increases by that. I hope that makes it clear. Okay. All right, so that's the interpretation here. Remember, it's a log odds, not the odds ratio. And this is the standard. And when you say that it increases by the every 1 milligram per deciliter unit increase in serum cholesterol increases the log odds of hepatomegaly by 0.21553%. In the bracket, you should, when you write your final paper, in the bracket, you should have the 95% confidence intervals as well, because that helps us. And you can add the 95% confidence interval and then comma p-value as well in the bracket, because it helps reader, and that's how you write the result section. It helps readers to understand if this number is statistically significant or not. When you look at the p-value, it surely is, right? And this is the standard error of it. Now, in order to write that confidence intervals, we need to find the confidence interval for the log odds. So how do we find that? We just say conf int model 1. Now, if you look at this is the confidence interval for the serum cholesterol. Now, if you look at this, for instance, is this a confidence interval? How do we know if this is statistically significant or not? If it crosses zero, it is not statistically significant, but this does not cross zero, so it is statistically significant. Okay, and then you can also look at the p-value as well, and you can, this helps us seeing if the results are precise. Again, the interpretation of the confidence intervals, we have covered that in theory, so I'll not go into depth. Okay, but this is how you get the confidence interval for the log odds. Again, I'll highlight that this is the log odds. um, and I'll come back to the different method of the getting the confidence intervals as well just in a while, but let's finish the interpretation of this one. So and then you get in the bottom that you get the null deviance and the residual deviance here. And that's also with the degrees of freedom, and it gives me the message that how many missing variables were deleted from the analysis, and the AIC values. Now this information, like what I've highlighted in here in blue, we use that to assess the model fit. Now, how do we assess the model fit? Is that, for instance, I'll give you a rough estimate. Again, there are no right or wrong answers. There are so many different ways you can pick the regression model. But when you add the like one, and we talked about the automatic selection, like the stepwise backward elimination, forward selection, and so on. But then we also then talked about in the last class very briefly. And again, this conversation should happen with biostats too, because it's a big giant topic in itself, how to select the models. But just so that you know, because I don't want to, like, I want you to give some sort of the foundation or idea for the in the biostats one as well. So if you decide or not take the biostats 2, then you still have some foundations to be able to continue or work on any project as well. Anyway, so when you add the predictor variables in the from if you go from simple to multiple multiple logistic regression, and if you add any predictor variable or the independent or the exposure variable in the model, I'm not going to say exposure variable because remember, it's in biostats we call the predictor, we call the independent variables, and so. But anyways, if you add a variable, I think residual deviance, for instance, it should drop by at least 2. If it does not, that means that that variable is not, it does not improve your model fit. So it's not significant variable that probably, I mean, you should decide to I mean, you could leave that out if that's what it means. AIC values, actually they're better to assess the model fit. For instance, is I think rule of thumb out here, the lower again here as well, the lower the deviance, the better it is. The lower the AIC, the better it is, right? So if again here you're looking at the drop of around 4 around 2 here as well, like when you add the variable, you're looking at the drop of at least 4. Okay, so if you add a variable, if it drops by 4, but again you have to be careful like how you build the model. But again, I'm just on these parameters, I'm just explaining these parameters can be used to assess the model fit. You can run a hypothesis testing on this null and the residual deviance. We'll look at that in a while. But again, just a little bit interpretations of the output that we get from the regression model. All right, so hope you know how to interpret the numbers now. See, it's pretty easy to teach how to build the model, but it takes more time to interpret the numbers correctly. Okay, so yeah, it is important. Now, if you look at this, for instance, if you can build the confidence interval with the model one here, but you can also use the confident default function, and it gives this number, and you can look at the difference. So what is the difference between the two? Difference between the two is that when you specify only the conf int, it uses the it gives the or builds the confidence interval based on the log likelihood function. Again, these are the slightly different concepts of the calculations to get the 95% confidence interval. But when you use the default function, it gives you the confidence interval using the standard errors that we discussed in the class. Okay, and so that's why you see sometimes when you calculate the standard errors and you're using the confidence function, it may not perfectly align. Your answer may be slightly different, but that is okay. As you can see, the difference between the two, it's very, very, very marginal. So it doesn't matter which one you use. For instance, if I were you, I would just go with the confident function, just this one as well. Or if you go with this one as well, doesn't matter. But I'm just showing you there are different options to get the confidence intervals. Anyway, so this is the confidence interval for log odds. Again, just like the linear regression, you can check the attributes, all the attributes of the model here, and you can call any attributes that you'd like. Uh, uh, but the big question is that, remember, the interpretation of logistic regressions, it's a little bit difficult, particularly when you're writing in a journal publication, or when the laymen have to interpret the results. The odds, the concept of the odds ratio itself is non-intuitive. It may it's a little bit difficult to understand or interpret. So particularly the log odds, it can be certainly challenging. So I would say in your paper, at least in your results sections, rather than uh, interpreting the log odds, I think you should interpret the odds ratios. Odds ratios are far more easier to understand and interpret than the log odds. Okay, so uh, so then how the question is, how do we get the odds ratio then? We get the odds ratio uh, by, remember, theory. Look at the formulas in the theory lecture that we talked about, that exponentiation, right? So what all we have to do is that, again, for instance, is if I have to just we talked about the attributes, right? But if I just want to have the coefficients of the model 1, I can type this coefficient of model 1, and it gives me the only the coefficients here, right? So what you need is that exponentiation of these coefficients. And this is where your basic concept, the basic knowledge of RStudio goes, is that RStudio can handle the analysis, the basic math. For instance, is I found out what is the log value of 1, and it gave me the answer, right? So the same thing, what we need here is that we need to exponentiate this coefficient. So either you can do is that copy this cholesterol concentrations coefficient value, put exponentiation and this number, and it gives you this answer. And this is your odds ratio for serum cholesterol concentration and hepatomegaly. Okay, so this is, but when you have multiple variables, rather than doing this manually, and it's also prone to errors, uh, you should let the RStudio handle that. So what it means is that you can tell that exponentiate these coefficients of model 1, and it gives the exponentiates uh, the the coefficients from that model, all of them. So for instance, it also exponentiates this intercept as well, but we are not going to repeat that or use that, right? So this is, and again, as you can compare that with the manual, uh, it's the same. Like if you're wondering like why it is 5.8, 5.5, it's just rounding. It's just a rounding, okay? But you get the same answer. So this is how you get the odds ratio. So now then we also need the confidence interval for the odds ratio as well. So it's the same concepts. Like if we use if this is the function that we use, then we just have to specify exponentiation in the function in the beginning, and put that in bracket, and that will give us the confidence interval for the odds ratio. And now if you see the odds ratio, the answer is this for the cholesterol and the hepatomegaly. Now, how do you interpret that? Again, does it, like, what is the value of no association here? It's a 1, because it's a now odds ratio. It's not the log odds. When odds ratio is 1, the answer is uh, no association. Why? Because it's a odds, when the numerator and the denominator are the same, that you get the answer 1, right? It does not cross 1, so that means it is statistically significant. Okay. But now, like, so this is the odds ratio. This is, sometimes you also want to just combine them in one table. You can do that as well using the cbind command function. So you just say exponentiation cbind. I want to bind this odds ratio, which is equal to this one, and then the confidence interval for the model. And once you run that, for instance, it gives you a nice little table of odds ratio 22.5% and the 97.5%. So like the two tails or the confidence intervals with the odds ratio in there. So you can see it in just one table. How do you get the p-value? P-value is from the summary of that model. And again, do we need to take the log value of these numbers as well? No, because the hypothesis testing, it doesn't matter if you do this or this, it doesn't matter, because remember, this hypothesis testing will stay the same. The numbers will stay the same irrespective of what your, because remember here the hypothesis will be log odds is equal to 0, but when you take the exponentiation, the hypothesis will be the odds ratio is equal to 1, but the answers will stay the same, right? So you can the p-values would stay the same. Anyway, so that's how you interpret the logistic regression. That's how you understand it. and that's how you run the analysis in RStudio. Anyway, so how do we assess the model fit? And again, this is just a very, very introductory uh, information here. So remember, we talked about the, let me call the model first here. Summary model one. And so this is the null deviance and the residual deviance. So one way to assess the model fit is that you can run the hypothesis testing on these two and see if this is statistically significant or not, the difference between the null and residual deviance. So what is the null deviance? Null deviance means is that when you only build the model just with the intercept, no variables at all, how does that model fit? Versus now this is the residual deviance, means that with when you plug in the variables predictors other than the intercept, how does that model fit? So, and that could be just the one predictor or the 10 predictors, right? uh, and on what degrees of freedom. So when you model fit, you can understand the take the first of all, I mean, the difference between the two, null and the residual deviance. You can do it with this function where you just say null deviance minus deviance, residual deviance, and you can see if you do the difference, this will be the answer. You can also do the difference between the residuals, sorry, degrees of freedom. Df means degrees of freedom for the null, degrees of freedom for the residual, and as you can see, the difference is one, like 1121 and 1120. So how do we run the hypothesis testing? You can do the chi-square between the two, and you want to see if the difference between the two is statistically significant or not. Once you run that model, it gives you the p-value that's saying that the model with the predictor variables fits better than the model, and that difference is significant. Then you just build the model just with the intercept. But again, this is not going to be much helpful, and I don't think you should be focused much on the final paper on this. So it's good to know, but it's uh, again, how you AIC values are used far more than doing this hypothesis testing. Yes, you can look at the deviance and how much it drops when you add the variable, but again, this is something that probably it's not going to be useful at this point. But again, that conversation will continue in the Biosatsu. Okay, so that's how we I hope this helped you understand the simple logistic regression. Again, now let's look at the here. Remember here our predictor variable was continuous, but we can also do the logistic regressions with the binary predictor variable as well. Like for instance, this TRT, we already changed that to factor variable, so I can run that. Remember, the condition for the logistic regression is that the outcome variable has to be binary. Okay, so I can still run this hepatomegaly, and now the export. So this is again what you have to do is that nothing different, the same what we discussed. I'm just now saying that model 20. Remember, I'm just showing you that it doesn't have to be in the sequence. I know previously I saved in model 1, but I can give any name that I would like. Okay, I'm saying that as a model 20 GLM, generalized linear model. Hepato is my Y variable, and I want to see the treatment, like it's randomized control trial. Like if that the medication is effective compared to the placebo or not in terms of the hepatomegaly, which one is better, right? Uh, so I just want to compare if the treatment is effective on the hepatomegaly or not. I'm going to run this. Family is binomial. You can specify the link is equal to logit as well. So how do you do that? Again, it's are not going to be super funky here, but it's always a good practice to specify in the codes, and then specify the link is equal to logit. You run the model. As you can see, the model ran, no errors. I can call the summary features to get the results. As you can see, this is the deviance residuals. These are the coefficients value, and this, as you can see, for instance, this is estimate for treatment group 1. As you can see, treatment 1, because there are 2 levels. So the treatment 1 here is that the drug. So reference group is placebo, which makes sense, right? So this is a standard error and the and the probability. As you can see, that it's between 0.05 and 0.10. You can say borderline significance. Well, it depends. We in statistics we usually use 0.05, 5%, right? So in that case, that is not statistically significant. So interpretation of this one, it's the same. Like for instance, what is interpretation now? X is this one is binary. That means that for participants who are prescribed penicillamine, uh, the log odds of hepatomegaly decrease by this number because it's minus, right? So it's decreased by this as compared to participants in placebo group. And this is on average, okay? And the 95% confidence interval, you include that and interpret that as well. So we talked about the interpretation, so I'm not going to discuss that in depth, but this is how we interpret that number, okay? Uh, Now, how do we get the odds ratio and confidence interval combined? It's the same thing. We talked about that. So this is the odds ratio and confidence interval. As you can see, it crosses one, so it is not statistically significant. So that means that here, the better interpretation is here. So the participants who were on this, who were randomized to penicillamine, the odds of developing hepatomegaly reduced by 0.15, around that, or 0.145 146 or something percent as compared to the participants who are randomized in the placebo group, with a 95% confidence interval of 0.72 to 1.02 with a p-value of 0.0886. Make sense? So that's how we interpret that. And so this is just, again, I'm showing you an example of the simple logistic regression with the binary predictor variable as well. And it could be multiple categories too. It doesn't have to be binary, but hopefully this helps you uh, interpret the numbers. When you have the binary, you have to think about what your reference group is. Okay, you have to be careful with that. And if it was like, for instance, if your reference group was indeed penicillamine, if this is the way you set, I mean, you can specify that, tell the R to set which your reference group you want to be, a reference level you want to be, but it doesn't matter. Like if even if your placebo was indeed if the penicillamine was the your reference group, then uh, the all it would happen was that the number would stay the same, but instead of plus, it would be the minus. So the interpretation would interpretation largely would stay the same. Okay. All right. Uh, so that's a model, but let's look at the multiple logistic regression, because again, we can use the simple logistic regression. You can see the p-value. If the p-value is less than 0.10 or 0.20, you can include those variables in the logistic regressions to begin your model with, and then you can decide which one you are going to drop or which one you are going to further add or not, right? So you can use the simple logistic regression for that purpose. But how do we build a multiple regression? Because, for instance, in this case, we saw that the treatment was not effective, statistically significant in terms of the reducing hepatomegaly. But the question is that, could that be because of some confounding effects that we didn't account for? Answer could be very well, yes. So let's control for some predictors. For instance, as we saw that previously the cholesterol was associated with this indeed hepatomegaly. So I just want to account for that, or that just for the cholesterol level. Um, Sex or gender may be an important confounder, age as well. uh, Again, don't look at the research question, I'm just giving some example. Okay, so what you have to do is just with the simple linear regression, you just add the plus in the equation and just add those, throw those variables in, and then the rest of the functions of the code stays the same, and you run the model. It builds the model, no error. You can call that summary feature and it gives you the output. Again, it's the same thing. It reminds you what your equation is, the distribution of the deviance residuals, and this is the output of your model. Like, for instance, you can see the treatment now is effective, reducing the risk of the hepatomegaly by uh, this is the log odds. Okay, this is not the odds ratio, and now it is statistically significant. And so does is the serum cholesterol, sex variable, and the age variable. Okay. Uh, Again, you can get the confidence interval. Like, I'll explain the how to interpret the estimate, not this estimate. This is the log odds, but I'm going to explain how to interpret the odds ratio for the from the multiple logistic regression. It's the same concepts. Remember, you get the confidence interval, but this is the confidence interval for the log odds because we didn't still exponentiate that. Okay, so you get the odds ratio by exponentiating the confidence interval. This is the odds ratio now. This is the confidence interval for the odds ratio, and you print them both, and this is what your model looks like. Uh, so, for instance, is what this means. What this now means is that let's just say first one minus. Oops. Let me copy this. 1 minus this number, so that means around 34.62. So what this means is that, and if you're wondering why did I do that, I'll explain that in a while. So that means the interpretation of this number means that the participants who are randomized into the into deep penicillamine medication uh, had uh, decreased odds, on an average decreased odds of developing the hepatomegaly by uh, 34.62%, right? That's your odds ratio. Uh, so this is the odds ratio, and this is the confidence interval. As you can see, this confidence interval does not cross is 1, so it is statistically significant. Um, and here the it's but here the big part, like how it is different from the simple logistic regression, is that this stays as constant. So in the beginning of the interpretation, that means that for a constant, or for the given cholesterol concentration, given age and sex, and then the interpretation of this number comes, because that means that you're accounting for the you are making these as constant, these variables as the constant, or you can say for a given cholesterol concentrations, given sex, or given age. Okay, either is fine, but that is when you're interpreting the results, make sure you include what that part in the interpretation. All right. uh, you can also, like, if you're bothered just mentioning this serum cholesterol, like every time, like the pulling the data set first and then using the dollar sign, you can actually attach the data set, and then you don't have to use these ones at all. That is okay, but it's not an ideal practice. Yes, it saves a lot of time, but if you make any changes in the data set, you have to attach that data set again. But I'm just showing that it says you can do that. Okay. Anyways, so that's how you build the multiple logistic regressions. That's how you interpret it. So hopefully now you are good to go for your final project. um, However, I wanted to end this lecture on some interesting aspect. Again, I need talked about that. For instance, let's look at our model. For instance, is the model that we built with model 20, right? That we built only with TRT, like this model that we only built with TRT. Where is that? Uh, yes, binary predictor, right? So we wanted to see if that randomization, the drug was effective or not. So we built this model 20. If you look at the summary of model 20, the AIC was 2612, the deviance was 2608. But the multiple logistic regressions that we built by throwing the cholesterol, sex, and age, for instance, is that model 2. If you call that summary, as you can see, the AIC is 1510 and the deviance is 1500. Significant drop, right? The model definitely seems a good fit. But again, there are more things that needs to be done. But anyways, this helps you understand, hopefully, the how do we use the AIC values in terms of the using the model. That is the most commonly used AIC than the deviance itself. Uh, but it's not uncommon either. Anyways, now I wanted to, this may be difficult if you don't have any statistical or epidemiology background. And if you have dealt with that, I think this may make sense. So it's okay. I'm not expecting you to include that in your final paper, but the students who are interested learning these, students will know that in theory, this is for you. And if you don't know, that's okay. Just go with it. You will learn the theory behind this in advanced epidemiology in the next term. Okay, if you're planning to take that. Interaction, this is a big part. So in this model, like in this model, what we talked about, that we control when we're looking to examine the association between treatment and the hepatomegaly, we control for cholesterol, sex, and age. So like we adjust for these confounders. But sometimes a third variable, it's actually not a confounder, it's an effect modifier. Or e- effect modifier means is that it modifies the effects between that variable. It distorts that. It's different than confounding effect. You'll understand the difference between the confounder and the effect modifier in advanced epidemiology. But if you know that, so how do we examine the if there is an interaction going on between the two variables or not? It's pretty easy. Interaction terms, what you have to do is that, remember, this was our previous model. All you have to do is that use the plus sign again, and then again, if I'm interested, if the gender is an effect modifier between the treatment and the hepatomegaly, what I'll use that is that this is my treatment multiplied with gender. So this is my interaction. This is my multiplicative. I'm examining the effect of the multiplicative interactions on this model between the treatment and the gender. You run the model, you see the summary. As you can see here, this is the interaction term that we included. And look at the p-value. Remember, don't interpret this number. It's not going to make sense. And again, we never use this coefficient. Remember, okay, that's something you will learn. And again, if I teach biostatistics too, I'll make sure to go in far more depth than this one. But always look at the p-values here first. It's not statistically significant, so I'm assuming that there is no interaction going on between treatment and the sex in my data set. But let's assume if this was statistically significant, then what you have to do is that not report this model, but you have to stratify your data set by gender or sex, and then report the treatment coefficient for males and the treatment coefficients for females separately. You have to stratify that, subset the data if this interaction was indeed statistically significant. If there was an interaction between these variables, that means that you have to stratify the variable or the results by gender and report them the results within each strata. That's how it should be done. But again, I just wanted to show you an example. It's super easy to conduct or examining the interactions in RStudio. Okay. Um and again, sometimes if the sample size is low, even though there is an interactions, you may not find it statistical significant, because when you stratify the data, it loses the some sort of the statistical power. So you need a reasonably good sample size in order to detect the interaction. That's the first thing. But sometimes some grants, they just require you to stratify the results anyways by certain variables, and gender is one of the more common one. So you just go ahead, subset your data set, and run the regression models, one for male and the one for female data sets separately. Okay, so that's a one way to do that. Anyways, so here, remember, the sex is a binary variable as well, and so does the treatment. But you can also examine the interaction between continuous and a binary variable too. The same concepts. I'm just now examining the impact between interaction between cholesterol and treatment. Run the model. As you can see, uh, the interaction term is again not statistically significant, so I don't have to worry about it. But again, if this was a significant, then again it becomes interesting, because now it's a continuous variable, and that's again, that conversation will continue in biostats too. But if you find, then if you are want to go ahead, again, I'm not expecting you to include in your final paper, but if you are really interested, curious, and if there is in literature, if there is a variable identified as an effect modifier, you can check that, and if that answer is yes, just report that there is indeed an interaction term going on in here. But if you find positive interaction, and you can do check the interaction between two continuous variables as well. Okay, to continuous variables too. But if that interaction is statistically significant, but then there are further there are some further steps that you need to take on when you report your results. All right, so but again, we'll continue. Again, that's a far more deeper conversation, but again, I just introduce and you to the concept of interaction or effect modifier. Sometimes in epidemiology, biostatistics, one field chooses interaction word, one field chooses effect modifier term better than other over the other. But again, it's the same concepts that you will learn in applied or advanced epidemiology. But hopefully this helps you a quick introduction to the topic, how you examine that in the regression model. All right. And again, if you had no idea what did I talk about, ignore. That's okay. That's okay as well. Okay. All right. With that, I'll conclude today's lab on the logistic regression. So hopefully, uh, you all now have what you need in terms of running the regression model. Again, hopefully this is not something that you'll have to add or change significantly in your paper. Remember, building the regression model is pretty quick. So hopefully it's not a big addition to your final paper as well, even though I know it's a short time for it's end of the semester. So hopefully it's not a too much work to add to your final paper. So with that, I'll conclude today's lab. And in the last lab, we'll be writing the R functions, which is okay. You don't have to, I don't think you'll make any changes based on what you learn in the last lab. It is just something uh, an advanced concepts that you will learn in RStudio that may help you run some deeper or in-depth or complex analysis for biosets 2, or later when you want to go farther beyond the basics in RStudio. Okay, so I'll introduce that topic and then I'll end that. So if you want to build up on that, you can on your own. Okay, so with that, I'll conclude today's lab. I'll see you indeed shortly, because I'm recording this at 10 a.m. and I'll see you in half an hour. for the first presentations, and I'm super excited about that. See you there.